Hiya Pirates! Today we're going to be talking about the concept of crystal lattices. Crystal lattices are what happens when ionic compounds are made. Now we've already talked a little bit about ionic compounds, but remember that sodium is an explosive metal. You put that in water and it catches on fire and it blows up. Chlorine is a green poisonous gas. If you breathe chlorine gas in, you die. But if you take explosive metal and green poisonous gas and put them together, you get something completely brand new, which is sodium chloride, which is just the salt that you put on your French fries. And that's not harmful to you at all, unless of course you have too much and have high blood pressure or something. So next time you have a chance to look at salt, look really closely at it and check it out. Can you see that the salt crystals make these tiny little cubes? Isn't that interesting? Do you think that they made it that way at the factory? Why would they bother? Well, the answer to that is no, they don't make the salt that way at the factory. It's not like they have a tiny little cubing machine. It's not for aesthetics. When sodium and chlorine go together to make sodium chloride, the atoms just know to make that shape. Well, how can that be? How can those atoms figure out how to make that shape? Well, remember, it's all because the atoms go together to make ions, which are charged. So remember what you got here is you start off with neutral atoms. So here's a sodium atom. If you check out your periodic table, sodium is number 11 and it's in the third row. So it's got 2 in the first shell there. It's got 8 in the second shell there. And then it's got 1 in the third shell, which is why it is an alkali metal in that first column in the third row. And then chlorine atoms have 17 electrons, 2 in the first, 8 in the second, and then 7 in the third, which is why, again, chlorine is in the 7th column, 7 valence electrons here in the third energy level or the third row. So when these guys start off, here is a sodium and here is a chlorine. And if I try to put these guys together to make a compound, nothing is going on here. I'm not getting any action here because they're not yet in a position to want to attract each other. But they have a trick up their sleeve. Why? Because of the octet rule. And the octet rule, remember, says that everybody wants to have 8 in their outer shell. So the sodium here is at 2, 8, and 1. So he's got an extra one that he doesn't want, right? So this sodium is sitting here with an extra electron, not doing anything. And the chlorine atom over here is at 2, 8, and 7. That one's not stable either because they want one more to get into that outer shell over here in order to make it stable with 8. So what do? Well, if they're not attracted to each other in this particular way here, then what they can do is they can transfer an electron. So this one electron over here from sodium can come over here to chlorine. And in doing so, we're going to take this last electron here that the sodium doesn't want anyway, we're going to give it to the chlorine. And in doing so, watch what happens. The sodium now becomes a sodium ion and gets a little smaller and becomes positively charged because now it only has 2 and 8. It has lost a negative electron, which is why it has become positive. The chlorine is going to get a little bigger than it was because now it's got an extra electron. It's got 2 and then 8, and now it's got 8 here. Get the ion going here. Sorry about that. Now it's a chloride ion. Now I've got 2, 8, and then 8 rather than 2, 8, and 7 there. And now this guy is positive and this guy is negative. And what happens when positives and negatives get close to each other? Well, positives and negatives, when they get close to each other, they now attract each other. But again, there's usually not just one sodium and one chloride, there's spagillions of them. And so consequently, when spagillions of them get together, they now can arrange themselves in such a way that they are attracted to each other and make a three-dimensional crystal out of things because they just kind of know how to go together to create a three-dimensional shape of a crystal lattice. So to show you an example of this, we can kind of try to simulate a crystal structure by the use of these magnets. Now this is not a perfect analogy by any stretch of the imagination, but it is going to get us kind of close to see what's going on. So what you've got here is you've got an ion that's there, and then you maybe have another ion that comes along with that. And I want to take a look at that. It just kind of knew to attach there. And then I can come along with a second one, and now all of a sudden I've got a different shape for those guys. And you can see that it kind of just knows where to go, and it is the best possible way for that guy to be together. So if I put another one on, it just goes there. And then I can start building a three-dimensional structure, and that three-dimensional structure with these guys just kind of puts them all together, and it kind of knows where it's supposed to go. So again, if I try to put some guys in there, it just knows how to create these different pieces, and it finds the best place for those ions to be, and it can arrange itself in a three-dimensional repeating structure based upon the size of the ions that are present. So again, it's not kind of perfect, but you can see that we have the basics of a three-dimensional structure here that is being created here by these different ions that are present. And all you got to do is put one in there, and it knows how to create it. So we are creating a real-life three-dimensional structure based upon the attraction and sizes of these different ions. So now that we've seen that these ions go together, positive, negative, in such a way that positive follows negative and negative follows positive, and they hook together because opposite charges attract, and they do this in a three-dimensional structure, we can see by the use of those little magnets that those ions just kind of know how to go together depending on the charge, size, and other factors involved with those particular ions. So salt isn't shaped into those cubes. Salt just knows to form those cubes. But keep in mind that cubes are not the only shape that are possible. If you, however, put potassium, aluminum, and sulfate together, you get these cool hexagon, I don't even know what you call. They're kind of like triangles with the tips cut off here. They make this shape there. I don't even know what that is. 2, 4. It's kind of a hexagon shape, but it's kind of a triangle with the ends cut off there. That's what happens when those ions get together. They just know how to make that shape. When titanium and oxygen get together, they make that shape. When calcium and carbonate get together, they can make all sorts of different shapes. And again, you've got all sorts of different shapes that are possible. But what we're here to talk about today is what the properties of those things are. And so what we are going to do is we are going to look into this new term, and this new term is here. It's called crystal lattices, right? And the important factor of a crystal lattice is this term right here, lattice energy. Now, there's a real technical definition that goes along with this, and if you're really interested in learning more about it, you can grow up and be a chemist and learn more about it. But for an introductory level of chemistry of what we're looking at here, basically, lattice energy is how strong the crystal is. If I have a high lattice energy, that means I have a strong crystal. If I have a low lattice energy, that means I have a weak crystal. So high lattice energy is strong crystal, low lattice energy is weak crystal. And with all of the different possible elements and all of the different possible ions, then we can have a great variety in the different crystal lattices and the different lattice energies that are possible. But just like we learned in the last unit, there are trends and there are patterns that we can pick up on if we are smart and look close. For example, let's take a look at this list here. Now, at first glance, it might look like it's just a bunch of ions and a bunch of numbers, but let's look a little closer. For example, if we were to look at these 4 compounds, what do you notice about all of those? They are all +1 and -1. Those are their charges. All the weakest +1 charge and the weakest -1 charge. And you'll notice that their lattice energies are in the hundreds. Now let's up the charges. In all of these next four here, we've got 2s. We've got a stronger positive charge, +2 instead of +1, and a stronger negative charge, -2 instead of -1. And what do you notice? Their lattice energy is in the thousands instead. And then if we look at our last two that are down here, we've got these guys here. Did you notice that the positive charge is even stronger at +3, while the negative charge remain the same, but we have a stronger positive charge? And check out the lattice energies. They are in the tens of thousands. So if you look closely at these guys, the charges make a real big difference on the strength of the crystal or the strength of the lattice energy. And clearly, the higher the charges, the stronger the crystal. +1s here were less than +2s here, were less than +3s here, according to their lattice energies over here, here, and here. The negative ones that were here were less than the -2s here in their respective columns. So the first rule that you need to know is a pretty darn simple one. High charge equals strong crystal. And that relationship is seen right here. +1 is weaker than +2, is weaker than +3, is weaker than +4. +4 is stronger than +1 over here. And the same is true for negative charges. -1 is less than -2, is less than -3, is less than -4. The weakest negative charge is -1. The strongest negative charge is -4. So the weakest possible combination that you can come up with is +1 and -1. The strongest possible combination you can come up with is +4 and -4, and then everything else in between. So the first rule is that the lattice energy is directly proportional to the ionic charge. The higher the charge, the stronger the crystal. After that, we have a secondary rule, and the secondary rule has to do with the size of the compound. So what we're going to do now is we're going to look at the halogens, and the halogens are these elements here: fluorine, chlorine, bromine, and iodine. All right, now check this out here. In these compounds, every single one of them is sodium. Sodium, 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 sodium. So you know what? I want to ignore the sodium. It's not good for comparison purposes in this particular case. What we're doing is we're looking at fluoride, chloride, bromide, and iodide as evidenced here, 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 and here. Do you notice that as you go down the periodic table from top to bottom, from here down to there, that the ions get bigger and bigger and bigger? So this is a bigger ion than this guy is here. It's a smaller ion. What happened to the lattice energy as the ions got bigger? Well, the bigger ion has a smaller lattice energy. The smaller ion up here has a bigger lattice energy. The smallest ion, fluoride here, has the biggest lattice energy. The biggest ion down here, iodine, has the smallest lattice energy. So that is an inverse relationship. The lattice energy is inversely proportional to the ionic size. The smaller the ion, the closer it is to the top of the periodic table, the stronger it is. And the larger the ion down here, the weaker it is. Now, there are reasons for this. There's something called Coulomb's law that you'll learn all about if you take physics and so forth. And things like charge density and all that kind of stuff. But that's really not what we're trying to get into right now. What we're trying to do is just kind of look for periodic trends and be able to recognize that those trends exist. So these are your two major features of ionic compounds. The first is that the lattice energy is directly proportional to the charge. The higher the charge, the stronger the crystal. And the second is that the lattice energy is inversely proportional to the ionic size. The smaller the ion, the stronger the ion, and the weaker the ion, the larger the ion that's there. Now we can see these things in more than just the lattice energy. Let's think about something a little bit more tangible than that, the melting point. Melting point is what temperature you've got to get to in order to turn the solid into a liquid, to basically rip the crystal apart. Take a look at some melting points here. Here are those same four compounds that we looked at before. Sodium fluoride, chloride, bromide, and iodide. Do you notice that the radius goes up, 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 and up, and the lattice energy goes down, 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 and down? What happens to the melting point as the lattice energy goes down? Well, take a look. They seem to kind of do the same thing. The 926 is the highest lattice energy that's here. It has the highest melting point. And then the lower lattice energy has a lower melting point, a lower lattice energy has a lower melting point, and a lower lattice energy has an even lower melting point. So the lattice energy and the melting point follow the same trend. High lattice energy, high melting point. Take a look at these that are here. These are based on the charges. This is a +1, -1. That's going to be weaker than this one that's a +2, -1. And then that's going to be even weaker than this guy here that's a +2, -2. Yeah, we can look at sizes and so forth like that, but we don't even need to. If the charges are different, you probably don't need to go further than that. So the +1, -1 that's here should be the weakest crystal. The +2, -2 here should be the strongest crystal, and those should follow along with their lattice energies and their melting points. So take a look. +1, -1 has a low lattice energy and a low melting point. A +2, -2 has a higher lattice energy and a higher melting point over here. So the melting point is directly proportional to the lattice energy. The stronger the crystal, the more temperature it's going to take to rip that guy apart. So, in conclusion, all of these things go together to make crystal lattices. The crystal lattices make different sizes and they make different shapes of these things. But the crystals, the strength of those crystals, the lattice energy is dependent upon the ionic charge, stronger crystal. And then the size, smaller ion, stronger crystal, weaker ion, bigger ion, weaker crystal. And the melting point goes right along with lattice energy hand in hand. If you've got a weak lattice energy, you've got a small melting point. If you've got a big lattice energy, you've got a high melting point. And that is crystal lattices.